The second part, the second part is direct and shear stresses. So what we need to do, guys, we have some loads, right? So in order to design our shaft, we want to find the maximum stresses. Okay, and in order to find those maximum stresses, we have to figure out what kind of stresses do we have. So normally on the shaft, we have bending stresses, we have torsion stresses or shear stresses due to torsion, and we have axial stresses due to those forces coming from the gears and so on. And then as a designer, as a shaft designer, you focus more on trying to find the shaft diameter or the factor of safety. And this is what we are going to do next. We're going to try to calculate the stresses and figure out how we can find the minimum shaft diameter or the factor of safety for our design. Okay, I'm sure that you have seen these equations before, but it is a quick review here that if you have a bending moment and a torsional moment on a shaft, so this is the equation that you use to calculate the bending moment, okay? So you have a shaft, and if you have only bending moment on this shaft, okay, then sigma x, which is the stresses in the x direction, if this is the x direction, is equal to the moment, bending moment, multiplied by y divided by I. And then this y and I is function of the geometry, okay? So the y is the distance between the neutral axis of the shaft. If this is, this circle is the side view of this graph. So this is the side view. So the distance here is y, okay? And if the diameter here is d, so the I here is the second moment of area. So the second moment of area is pi multiplied by d to the power 4 over 64. But remember, this is for a solid circular cross section, which is normally the case in our shaft. And also here we have shear stresses due to torsion, because the same shaft can be exposed to torsion because we are going to transmit some power. So, and this power is going to cause the shaft to rotate, or we are going, while we are transmitting the power, the shaft rotates and it is subjected to torque. So tau xy here, we normally call it, it's TR over J. Again, T is the torque and R and J are function of the geometry. If this is again the cross section of the shaft, so this value is the R, which is the distance between the center of the shaft to the outer fibers of this material, and J is the polar second moment of area, which is pi d to the power 4 over 32. Then we can just simply say, okay, for a circular cross section, we can substitute these values, these three values here. We can substitute these values into equation 1 and 2. When we do that, we have sigma x and tau xy, which is the, here is the, we call it direct force or normal force, and here we have shear force. So if we have a shaft and this shaft is subjected to both bending and torque, which is going to be the case, we can use these two equations to calculate the direct stresses or the normal stresses and the shear stresses. And you see here sigma x is 32m divided by pi multiplied by the diameter of the shaft, or the outer diameter of the shaft to the power 3, and tau xy, which is the shear stress here in the xy direction or the xy plane, is 16t over pi d to the power 3. So these are the two types of stresses, and they are two different types of stresses. One is direct stress or normal stress, and the other one is shear stress. So we need to kind of combine them together. In order to combine them together, we come up with what is called the principal normal stresses and the shear maximum, the principal shear stresses. So principal normal and principal shear stresses. So in this case, sigma y is equal to 0. We don't have any stresses in the y direction. If we consider this is x and this is y, so we don't have any stresses in the y direction in this case. That's why we can just find the principal normal stresses sigma 1 and 2 using this equation that I'm sure that you have seen in design analysis 1. right? So, and also if you substitute sigma x and tau xy from the previous slide into this equation here, number 5, you will just come up with the principal normal stresses sigma 1 and 2, where sigma 1 is the maximum normal stress, sigma 2 is the minimum normal stress, which is 16 over pi d to the power 3 times m, where m here is the bending moment on the shaft, and T here is the torque on the shaft. The principal shear stresses is only this bracket, and then it is the plus or minus, plus goes for the maximum, negative goes for the minimum, and then it is plus or minus the root tau xy squared plus sigma x over 2 squared. And again, if you, from the previous slide here, you just substitute sigma x and tau xy into this equation number 7, then you will just come up with the maximum shear principal stresses tau 1 and 2. Okay, so now we kind of try to think about how we are going to use this to find our diameter, the diameter of the shaft. Okay, which is the variable, the design variable that we are trying to find. So we can use what's called failure criteria. Failure criteria, we have 2 failure criteria here. The first one is the distortion energy theory, and the second one is the maximum shear stress theory. So the distortion energy theory, or von Mises theory, stress theory, is as follows. So you have the equivalent stress here is equal to sigma 1 squared plus sigma 2 squared. So sigma 1 and sigma 2 are the normal stresses, or the maximum, from here, the maximum principal stresses, the principal normal stresses. So coming back to here, so you have here the principal stresses, sigma 1 and sigma 2. But here, remember, if you use this equation, tau xy, it's just tau xy. It's not the principal shear stress. It is this tau xy. It is equation number 4. This is one form of the equation. To the power 1/2 is greater than or equal the S yield, or the yield strength of the material. It's a material property divided by the factor of safety. Then in this equation, if we have only moment, bending moment, if we have only bending moment and torque, so we can substitute equation 4 and 5, go back. So this is equation number 5, okay? And this is equation number 4. You substitute these 2 equations into here, sorry. So we just come up with equation number 9. So if you substitute equation number 4 and 5 into this equation, then you come up with this equation number 9, which is 16 over pi d to the power 3 multiplied by 4 multiplied by the moment squared plus 3 times the torque squared to the power 1/2 is greater than or equal the yield strength of the material divided by the factor of safety. Okay, and based on this equation, we can try even to simplify it to find either the diameter that we are looking for or to find the factor of safety. Okay, so on the next slide, so you see here that the torque normally it is not explicitly given. So the torque is equal to the power that is going to be transmitted divided by omega, which is the angular velocity. So the torque can be calculated using this equation, and the bending moment, you need to think about the bending moment diagram and try to find the maximum bending moment. Then the previous equation using the distortion energy theory criteria, we can use it to find either the diameter or the factor of safety. So normally, if you are going to use the distortion energy theory, so in this case, you are going to use this equation to find the diameter, or this equation to find the factor of safety. And this is the minimum diameter that you are going to find. So the second and most important failure criterion is the maximum shear stress theory. And this is even simpler because normally what we have here, we have sigma 1 minus sigma 2, which are the principal stresses, maximum principal stress, minimum principal stress. So the absolute value of this difference is greater than or equal to S yield over the factor of safety. If we have only a bending moment M and torque T on the shaft, so we can use this equation. We can substitute the values into this equation here, or substitute the values from equation number 6 here to have this equation. So we need sigma 1 and sigma 2 actually. So you go back here all the way down to here to this equation. I should have said, oh, this equation number 6. So go to this equation, substitute the value of sigma 1 and sigma 2 from here to here. So, and then you will get this maximum shear stress theory. And then again, this equation can be used to either find the minimum diameter or the factor of safety. Okay, so this is the equation if you are going to use the maximum shear stress theory. So the results, the stresses that we have just tried to find now are the result of the applied loads. Okay, and for ductile materials, we should normally use the maximum shear stress theory. So we should normally, if we are going to use ductile material for the shaft material, which is going to be the case, we can use either one of these two equations to calculate the diameter or the factor of safety. Okay. Also here, we are talking about the twist. You remember if you have a torque, so this torque makes the, or just twists the shaft. So this equation here gives you the angle of twist. So the angle of twist theta is equal to the torque multiplied by the shaft length, and here the shear modulus multiplied by the polar moment of area. Then there is some, this theta that you're going to calculate should be less than or equal to 3 degrees for every 1 meter. So every 1 meter of the shaft should not exceed 3 degrees. So you need to calculate theta, then convert it from radian to degrees, and then consider the length of the shaft to find the permissible angle of twist if you want. And then based on that, you can, from here again, the variable that you are trying to find is the diameter of the shaft that gives you this kind of a twist, or within this limits. Okay, right. So so the factor of safety, the factor of safety here actually reflects the designer confidence in the data used. So sometimes we make some assumptions in our design. Sometimes we think about the consequences of failure as well. Some components, when they fail, they only just break some local things, but some other components, if they fail, it means lives and a lot of money. So you need to think about a higher factor of safety. Also, when we calculate load magnitudes, there are some uncertainties in calculating the loads. In material properties, when we characterize the material, we have some errors in the tests and experiments as well. Manufacturing processes are not exact as well. So we have some sort of service conditions that might change. The load might change a little bit due to the service of the system. So all these things feed into the factor of safety. In general, the factor of safety is in the range between 1.25 to 4, but for general application, we can use a factor of safety of 2. So possibly we'll just focus on this, just use a factor of safety of 2 for a material yield based on the material yield strength. So when we say S yield over factor of safety, so this can be based for general application.